Hi, everybody. Good to be back again. I'm going to break this down piece by piece here on the meaning code, back to the entropy problem. So I'm listening again to the Stephen Wolfram conversation with Lex Friedman, and I'm hopeful that they will keep it up here, that I am using a link to Lex Friedman's podcast. I'm hopeful that he won't take me down. So I'm going to go over just the first 5 minutes of it. And I'll share a screen here. Optimize sound. And here's the video. We have this little problem with the sound on my thing here. It doesn't show up until halfway through. So let's try this.
Almost 20 years ago, you published a new kind of science where you presented a study of complexity and an approach for modeling of complex systems. So let us return again to the core idea of complexity. What is complexity?
I don't know. I think that's not the most interesting question. It's like, if you ask a biologist, what is life?
Yeah.
That's not the question they care the most about. What I was interested in is, how does something that we would usually identify as complexity arise in nature? And I got interested in that question like 50 years ago, which is really embarrassingly a long time ago. And, I was... how does snowflakes get to have complicated forms? How do galaxies get to have complicated shapes? How do living systems get produced? Things like that. And the question is, what's the sort of underlying scientific basis for those kinds of things? And the thing that I was at first very surprised by, because I've been doing physics and particle physics and fancy mathematical physics and so on. And it's like, I know all this fancy stuff. I should be able to solve this sort of basic science question. And I couldn't. This was like early, maybe 1980-ish time frame. And it's like, okay, what can one do to understand this sort of basic secret that nature seems to have? Because it seems like nature, you look around in the natural world, it's full of incredibly complicated forms. You look at sort of most engineered kinds of things, for instance, they tend to be, we got sort of circles and lines and things like this. And the question is, what secret does nature have that lets it make all this complexity?
Okay, so the first thing to notice is that he has an underlying assumption that nature has secrets. And that underlying assumption drives the direction of his study and the direction of his passion. Now, interestingly, when you get to the end of this conversation, which is 3.5 hours long, he tells Lex Friedman that in the early 1980s, he was the one who actually started the whole complexity science movement. And since then, now there's like, I don't know, he named some huge number of complexity institutes that are all over the world looking at these questions. But now that he is on the other side of that, he doesn't see complexity as the main thing. He goes one layer down from that, and he's looking at computation. Now, if you've watched all the videos that I've done with Glenn, you know that Glenn also feels that computation is fundamental. And when he first said that, it kind of scared me, because I thought he was saying like, the world is a computer, which sounds very cold and clinical and not at all like the way I imagine God working. But when you understand I don't know exactly what Wolfram is talking about when he talks computation being fundamental, but I do know what Glenn means, because I've talked to him for like 12 hours now. And when he's talking about computation being fundamental, he's talking about the very simplest kind of a computation is, for example, a key fitting into a lock. And the lock has to be of the right conformation for the key to fit. Well, I put it the other way, the key has to be the right shape to fit into the conformation that is already in the lock. So everything that works has to work based on some pre-existing structure. So to say that computation is fundamental means that there is already some sort of structure there that the thing fits into.
We, in doing engineering, for example, don't naturally seem to have. And so that was the kind of the thing that I got interested in. And then the question was, could I understand that with things like mathematical physics? Well, it didn't work very well. So then I got to thinking about, okay, is there some other way to try to understand this? And then the question was, if you're going to look at some system in nature, how do you make a model for that system, for what that system does? So, a model is some abstract representation of the system, some formal representation of the system. What is the raw material that you can make that model out of? And so what I realized was, well, actually, programs are a really good source of raw material for making models of things. And, in terms of my personal history, to me, that seemed really obvious. And the reason it seemed really obvious is because I just spent several years building this big piece of software that was sort of a predecessor to Mathematica and Wolfram language, a thing called SMP, Symbolic Manipulation Program, which was something that had this idea of starting from just these computational primitives and building up everything one had to build up. And so kind of the notion of, well, let's just try and make models by starting from computational primitives and seeing what we can build up, that seemed like a totally obvious thing to do. In retrospect, it might not have been externally quite so obvious, but it was obvious to me at the time, given the path that I happened to have been on. So, so that got me into this question of, let's use programs to model what happens in nature. And the question then is, well, what kind of programs? And, we're used to programs that you write for some particular purpose, and it's a big, long piece of code, and it does some specific thing. But what I got interested in was, okay, if you just go out into the sort of computational universe of possible programs, you say, take the simplest program you can imagine, what does it do? And so I started studying these things called cellular automata. Actually, I didn't know at first they were called cellular automata, but I found that out subsequently. But it's just a line of cells, each one is black or white. And it's just some rule that says the color of this cell is determined by the color that it had on the previous step and its two neighbors on the previous step. And I had initially thought that's, sufficiently simple setup. It's not going to do anything interesting. It's always going to be simple, no complexity, simple rules, simple behavior.
Okay, so one of the things that stands out to me here is when he's talking about the changes that take place in the cellular automata program as it goes on, they're all relational. It depends on what the relation was between what was next to it and what comes after it. So keep that in mind. All these changes are dependent on relationship.
Then I actually ran the computer experiment, which was pretty easy to do. It probably took a few hours originally, and the results were not what I'd expected at all. Now, needless to say, in the way that science actually works, the results that I got had a lot of unexpected things, which I thought were really interesting. But the really strongest result, which was already right there in the printouts I made, I didn't really understand for a couple more years. So it was not, the compressed version of the story is you run the experiment and you immediately see what's going on. But I wasn't smart enough to do that, so to speak. But the big thing is, even with very simple rules of that type, sort of the minimal, tiniest program, sort of the one-line program or something, it's possible to get very complicated behavior. My favorite example is this thing called Rule 30, which is a particular cellular automaton rule. You just start it off from one black cell, and it makes this really complicated pattern. And so that, for me, was sort of a critical discovery that then kind of said, playing back onto, how does nature make complexity? I sort of realized that might be how it does it. That might be kind of the secret that it's using, is that in this kind of computational universe of possible programs, it's actually pretty easy to get programs where, even though the program is simple, the behavior when you run the program is not simple at all. Mm-hmm. And that was...
So here's another thing to keep in mind, and I'd love to have you put something in the comment section on this. Simple rules do not equal simple behavior. And where else do you see that in life and in the universe? So I'd love to get a discussion going on that. I think that's a really interesting question.
So for me, that was the kind of the story of kind of how that was sort of the the indication that one had got an idea of what the sort of secret that nature uses to make complexity, and that complexity, how complexity can be made in other places. Now, if you say, what is complexity? It's complexity is, it's not easy to tell what's going on. That's the informal version of what is complexity.
But there is something going on. But it's
there's
not
a
easy
rule.
to know what.
Right.
Well, no, the rules can generate just randomness, right?
Well, that's not obvious. In other words,
that's not obvious. That's right.
It's not obvious at all.
Right.
And it wasn't what I expected. It's not what people's intuition had been and has been for a long time. That is, one might think you have a rule, you can tell there's a rule behind it. I mean, it's just like, the early, robots in science fiction movies, right? You can tell it's a robot because it does simple things, right? Turns out that isn't actually the right story, but it's not obvious that isn't the right story because people assume simple rules, simple behavior. And that the sort of the key discovery about the computational universe is that isn't true. Mm-hmm. And that discovery goes very deep and relates to all kinds of things that I've spent years and years studying. But that in the end, the sort of the what is complexity is, well, you can't easily tell what it's going to do. You could just run the rule and see what happens, but you can't just say, oh, show me the rule. Great, now I know what's going to happen. And the key phenomenon around that is this thing I call computational irreducibility. This fact that in something like Rule 30, you might say, well, what's it going to do after 1 million steps? Well, you can run it for 1 million steps and just do what it does to find out. But you can't compress that. You can't reduce that and say, I'm going to be able to jump ahead and say, this is what it's going to do after 1 million steps, but I don't have to go through anything like that computational effort.
By the way,
so you'll notice here that what he's saying basically is that the universe cannot be deterministic, because if it were deterministic, they could determine where all the atoms and particles are right now and where they're going to be 1 million steps from now. But that's not the way it works. Basically, he's saying, people say, show me the rule and I'll show you what will happen. And he says, that's not true. You can't compress it. You just have to let it run all the way out. And doesn't that look just like life? I mean, that's the way our lives are. We might have a certain plan. We make plans and we think this is what I'm going to be doing 5 years from now, but something intervenes and we end up doing something entirely different, which may or may not be better than what we had planned originally. So the other thing that I think is very, very interesting is when you have this potential unknown complexity that arises from even the simplest rules, that is a very good reason only to have the very minimum number of rules possible. So the other thing that occurred to me is when he's talking about computational irreducibility here, basically he's hitting on this thing that John Vervaeke is always talking about, of combinatorial explosion. There are too many choices. There are too many options. There's too many things that could happen. There's too many unknowns involved. And that got me to thinking, well, you know how Glenn always talks about how entropy is this sort of forgetfulness of the universe when there are too many states in which things could be. There's not enough information to put it back together again. And in other words, there's too many knowns in this forgetfulness of entropy. And there are too many unknowns in the combinatorial explosion. So in the comment thread, if this gives you any ideas, I'd like to think about how combinatorial explosion might be linked to entropy. So that's about as far as I'm going to go today. And I'll try to pick this up again in the near future. In the meanwhile, I have a really great conversation coming up with John Crosby that's going to publish on Sunday morning. So be looking out for that. Have a great day, everybody.